Okay, I'm going to pick up where I got interrupted. The video cut off and I don't know why. So down here at the bottom, all I was saying is we know from -3 to 3 I converge absolutely. But what I don't know is, do I converge at the endpoints? So let's take a look at, and this holds for everything. We say the alternating harmonic series is convergent based on the Leibniz's theorem. But we know that the series, such as 1 over n, is divergent to the p series. Since we have a mismatch, we say alternating harmonic series is conditionally convergent, or converges conditionally. So again, visually, I know if I give you this series, by Leibniz's theorem, we converge. But u sub n equals 1 over n is a divergent series. So since we have a mismatch, we say that our series of the simple harmonic series is actually conditionally convergent. Okay, I'm going to go and turn the lights on. So let's do this a little more formally. Prove the alternating harmonic series is convergent, but not absolutely convergent. And then we're asked to find a bound for the truncation error after 99 terms. So we're going to be using that definition for error on the previous page. So alternating harmonic series is going to look like this. Summation n equals 1 to infinity minus 1 to the n plus 1 all over n. And the terms will look like this: 1 minus a half plus a third minus a fourth, and so on. So based on what we saw from Leibniz's, I isolate every part of this expression that's not alternating. That gives me my u sub n. So my u sub n is 1 over n. So now I'm going to run Leibniz's theorem. 1, 2, 3. You'll see me every time I do these problems, I write 1, 2, 3. That way I don't forget that I need to do everything. Okay, so first of all, each u sub n is positive. Yes, without the alternating term, this would be 1 plus a half, a third, and so on. So I've got that one correct. The next one, we look at u sub n greater than or equal to u sub n plus 1. So this is like saying the terms are decreasing. If I consider this to be u sub n, and this is u sub n plus 1, u sub n is bigger than u sub n plus 1. So I do check out number 2. And then finally we take the limit as n goes to infinity of u sub n. So in our case, that's the limit of 1 over n, and this definitely goes to 0. So by Leibniz's theorem, we converge, but we have a mismatch because I know the series 1 over n diverges. Therefore, when we have this conflict, so we are conditionally convergent. Let's run through a regular example, something that's not the alternating harmonic series. So here we go. -1 to the n, 1 plus the square root of n. So let's write out that we're going to use Leibniz's theorem. And my u sub n will be every part of this that's not alternating. So that's 1 over 1 plus the square root of n. And if I write out a few of these terms, I'm going to get something like a half plus 1 over 1 plus the square root of 3 plus 1 over 1 plus the square root of 4. And estimating these values, this is going to be 0.5, this is going to be 0.333, and this will be somewhere, something 0.4-ish. So the terms are getting smaller. So since we're running Leibniz, I'm going to do 1, 2, 3. The u sub n's are all positive, kind of by default, so check. U sub n plus u sub n is greater than or equal to u sub n plus 1. The terms are getting smaller as we add terms, so we got to check on that. And if I take the limit as n goes to infinity of 1 over 1 plus the square root of n, then I know this goes to 0. So by Leibniz's theorem, 1, 2, 3, check out. We converge. So you always should check for a mismatch. So I'm going to run the direct comparison test. I could run whatever test I want. I'm going to do direct comparison test. So I'm going to start off by saying the square root of n is less than the square root of n plus 1. I can take the reciprocal. 1 over the square root of n then would be less than 1 over the square root of n plus 1. And this is showing me that a sub n is greater than d sub n. So since 1 over the square root of n is divergent, then our b sub n, 1 over the square root of n, or our a sub n, must also be divergent by the direct comparison test. Therefore, we have a mismatch, and that leads us to believe that a sub n is, again, conditionally convergent. So as we move forward, we're going to be following the process on the next day. How to test a power series for convergence, including the endpoints. So here's a process we're going to follow. We're going to use the ratio test to find a value for x for which the series converges. So it'll either be all reals, one value, or we'll get some IOC. Like this is trying to show you here in a mathy way that tends to be confusing. So this also, so it reminds me, sometimes we only converge at a point. The IOC from the ratio test tells us where we converge absolutely. What is uncertain is whether or not there is convergence at the endpoint. That is why we test each endpoint in the series. So in steps 2 or 3, we're actually going to take the value of x. Let's say this is our interval of convergence. We're going to take that value and plug it into the series for x, and we will generate a new series, and we will test that new series. So if the interval of absolute convergence is finite, test for convergence or divergence at each endpoint. If the ratio test fails at these points, so instead we use a comparison test, their integral test, or the alternating series test. If the interval of absolute convergence is this, conclude that the series diverges when we're outside of that interval, because for those values of x, the nth term does not approach 0. So basically we're saying once you've determined what's happening at the endpoints,